actually, simply compute what the residue would have been in the S channel, and then multiply by 1 over S, and then add the other channels. Okay, so that sounds like a trivial thing to do. When you have particles with spin, it starts being non-trivial for the following reason. If, for example, for a particle of spin curly S, I compute the residue in the S channel, I find that that residue in the S channel itself has a pole in T. Okay? And that means that it's not trivial. If I now multiply this by 1 over S, now I'm T channel pole out, right? Now, fortunately, it does. And that's the easiest way to determine the 4-particle Yang-Mills amplitude. Now, if you go to spin 2, it has a pole that goes like 1 over T squared, which sounds bad because it's a double pole, which is illegal. But you have to remember this is when S is going to 0, so that T squared could be the same as a negative 1 over TU. And again, if you multiply by 1 over S, that has a chance of working, and in fact it does work, and that's how you determine the gravity amplitude. And this is a way of doing this calculation really essentially directly by finding the object that factorizes correctly. But if you go to a higher spin, you see that it's just impossible, okay? Because it would be 1 over T cubed, and then it's simply impossible. That's, you have to have double poles or higher poles in one channel or another. Now that just shows that you can't have massless self-interacting spins, but in fact massless higher spin particles are ruled out directly simply by the existence of either photons or gravitons. Photons if they're charged, gravitons period, okay? For example, if we look at Compton scattering for a charged particle of spin S, we do the same exercise. We look at the residue in the S channel, we find that as a U channel pole with a power that's simply too hot in the denominator. You have to have a double pole, and that's impossible for spins greater than or equal to 3/2 already. Charged particles of spin greater than or equal to 3/2. So you can do this exercise more generally and discover that the only possible consistent 4-point interactions correspond to the usual theories that we know and love. You discover supersymmetry, gravity is unique. These statements contain in them all sorts of other things. They contain the Coleman-Mandula theorem, they contain the Weinberg-Witten theorem. All of these things are part of this basic, simple 4-particle check. So that's the story for massless particles. Their dynamics almost completely fixed. We didn't have to write down Lagrangians or imagine, talk about gauge redundancies or anything like that. Just directly build them. A lot of work over the past 10, 20 years has been in these kinds of ideas to any number of particles, any number of loops, many different kinds of theories. But today I want to talk about another aspect of it, which, yes? That's what I'm going to talk about. I'm going to talk exactly about how to do S-matrix theory with general mass. Yeah, this is now the outline for the rest of the talk, okay? Because the other thing that we discover is that these amplitudes that we just computed for gravity blow up in the ultraviolets, I want to fix them somehow, okay? And as we'll see, I'll review in a moment, there's a general, on very general grounds, any UV completion for any theory that has long-range forces, gravity, Yang-Mills, phi cube theory, doesn't matter. Any such thing cannot be UV completed with a finite number of particles and a finite number of spins in a weakly coupled UV completion. You have to have an infinite number of particles, an infinite tower of spins, and that's one motivation to figure out how to deal with the S-matrix formalism for any mass and spin. Another motivation is to talk about the standard model and talk about all these things for real physics. Okay, so those are both motivations. Sorry? No, but we certainly have to talk about mass, right? And it depends. If you want complicated glue ball scattering, then you would have to do that as well. Of course, that doesn't happen in the standard model, but anyway. Okay, and then I want to talk about the general UV completion rules and the really magical way that string theory solves them. We'll make a very sharp conjecture that string theory is a unique answer to this problem of UV completing at least gravity. Certainly isn't for general scalar theory, or Yang-Mills theories will do, but there's at least a very precise conjecture that the answer is unique for perturbative gravity amplitudes. And in this whole subject, you're going to see that the biggest, most non-trivial fact is unitarity. And this implies various absolutely miraculous positivity properties of residues of string amplitudes, things that we have indirect proofs for from the no-ghost theorem, But if you want to imagine there's another picture for determining the amplitudes ab initio, you need to come up with some picture for why those identities are true. And they're incredibly non-trivial, very simple to state. They're very non-trivial. I'll show you some of them. But it gives a flavor that you might try to look for a more algebraic picture for determining these objects where the unitarity is an output and isn't something that you have to check. Checking it is so ridiculously non-trivial. And if I have time, which I probably won't, I'll give you a version of this much more algebraic way of thinking about things, which is based on a paper that just came out before Christmas on a rather different way of thinking about what the gravity and Yang-Mills theory S matrices are, which is much more algebraic, where locality and unitarity are outputs out of more algebraic constraints. All right, but I probably won't have a chance to get to that. All right. So let's first talk about S-matrix rules for general mass and spin. And these rules are very easy for external scalars, simply because no matter if you have a spin S particle in any number of dimensions, there's just a unique way that there's a unique structure you can write down to contract the polarization vector for this guy with the external momentum. And if you exchange this particle, if you exchange a massive particle to compute a residue in some channel, what you get are the Lejeune polynomials as a function of cosine theta in d dimensions, and the generalizations called the Gegenbauer polynomials in 3 dimensions, the Gegenbauer polynomials in d dimensions. But all of that is that way of thinking about things starts getting much more complicated when you have spin on the outside, and for a variety of technical reasons. But it's really a conceptual thing is the problem, is that we're not really labeling states in a way that makes the transformation into the little group manifest. Okay, so if you think about it, when we label a massive spin 1 particle by saying it's a polarization vector that's transverse, epsilon dot p equals 0, well, again, it's not as bad as when you have a gauge redundancy where you further have to have a gauge redundancy on the polarization vectors, but it's still not completely invariant, right? You have this constrained object. It's even worse when you have a spin 1/2 particle, right? We have gamma matrices, we have 4-component Dirac spinners. Why? All of these things are an artifact of the field picture, calculating these things from a quantum field theory, where those things like epsilon dot p equals 0 or the Dirac equation are the equation of motion for the external fields. And they're not telling you, it's really crazy to drag a 4-component object around to describe the 2 spin components of an electron. So what we'd like to do is just do what we did with massless particles and make the action of the little group manifest. And this is incredibly simple in 4 dimensions. We saw already the little group for massless particles is U1. For massive particles, it's SU2. So life is as simple as it could possibly be, and we should take advantage of that fact. And the Arps of SU2 are naturally labeled just by spin S, symmetric spin S tensors. But the idea is that precisely because the little group leaves the momentum invariant, and the momentum is an alpha and an alpha dot x, I can use the momentum, if I like, to transfer all the indices to either all alphas or all alpha dots. This formalism is naturally chiral. That's good. The real world is chiral. Okay, and so that's it. So that's just kinematically. That's how we label the external states. They're just labeled by symmetric tensors with 2s indices. Okay, so that much is essentially trivial. But where it starts getting fun is that we can go back and do exactly the same exercise we did before and completely determine what all the 3 particle amplitudes are. Okay, so we can go through them one by one. Here's the case with two massless and 1 massive. Okay, so I need to have something that has 2s of these indices. So I have the lambda for this particle and for that particle. And so I just write down the appropriate numbers of lambda 1, lambda 2, as well as these spinor brackets that have the correct helicity weights, and I'm done. Okay? So precisely just as for in the massless case, this structure is totally unique. Once you specify the helicities of massless particles, there's one amplitude you can write down up to a coupling constant. This trivializes things like Yang's theorem. Okay? Yang's theorem says that massive spin 1 particle can't decay to 2 massless photons, and that's just trivial. That follows from the fact that these numbers have to be positive, because they tell you how many lambda 1s and lambda 2s you have to have. And also, the other headache in the polarization vector language is when you exchange a particle, you have to sum over polarizations and take out traces. And it's that combinatorial act of taking out traces that gives you the Gegenbauer polynomials. But here there's nothing to do because there's no constraints on these guys. It's a purely combinatorial thing. You just hook up the indices on one side and the other. And so these are all the polynomials that ever show up, the spinning versions of the Gegenbauer polynomials in 4 dimensions. And they have this very nice, very combinatorial flavor to them. You might not recognize normal Lejeune polynomials, but there are indeed representations of the normal Lejeune polynomials which look exactly like this. All right. Now, the most conceptually interesting case is when you have 2 massive and 1 massless. And now I need to have something which has just an index. I just have the lambda of this guy available. I can only use the momentum of 1 or 2 times the lambda tilde of the massless guy. And so dimensional vectors that build the objects that I'm interested in. If the masses are unequal, then this inner product is m1 squared minus m2 squared, so these guys form a basis. And so that's it. That's all the 3 particle amplitudes. You write down some number of u's, some number of v's, and just the correct numbers have the right helicities, and you're done again. If the spins, just for fun, if the spins are the same, you have 2s plus 1 different structures. And these, roughly speaking, correspond to all the magnetic moment type couplings that you can have between different states. What's really interesting is the case when the masses are equal. In this case, this is not a basis. UV is 0. So I have the lambda, I have the epsilon symbol. But I have one more bit of information, which is the constant of proportionality between this V and U. Okay? And that constant of proportionality has little group weight. And once again, if I have 2 particles of equal mass, I write down some number of these U's now, some number of epsilons between the 2 sets of indices. By symmetry, they can only link, because these are symmetric indices, the epsilons can only link one side to the other. And some number of powers of this x. And this x is where the excitement happens, where a lot of the constraints that we saw in the massless case are sitting here, even when things are massless, because this x object is not local. There's no local formula for this variable. That's reflected in the small massless case in that the 3 particle amplitudes had denominators, and that was the origin of those funny poles in the channels when we glued things together, and exactly the same thing is happening here. All right, let me just give you some examples. So let's say you just have a scalar coupled to a photon, then the 3 particle amplitude is just x. Okay? The electric charge times mx. What about a spin a half particle? An electron, well, there's 2 structures now. One of them is mx times epsilon alpha beta, and the other one is the 2 lambdas. Okay, and that's it. So x is just a number. Yeah, it's just a scalar, right. So this thing is the electric charge. This new structure here is the G minus 2 of the electron. And in general, if you have a spin s particle, you have 2s of these G minus 2s and one electric charge type coupling. Anyway, the story for 3 massive is really trivial, and I won't go through it in detail. So really, the really non-trivial cases would equal masses coupling to a massless particle because you have a non-local object. The rest of it is just is basically trivial. But now we're done. Now we have a concrete 4-point challenge, which is given some spectrum of masses and spins and couplings. We need to find the class of all possible 4 particle amplitudes which factorize correctly. Okay. Now, again, most naively, what you can do is just what we said before. Take 2 of the 3 particle amplitudes, glue them together, find the residue, multiply by 1 over s minus m squared, and add the different channels. And you can do this for things that look naively scary, like this process. A top quark bangs into a photon, produces an excited top quark of spin 3 halves that goes back to a graviton and comes out to a top quark. This is something that's actually utterly trivial from this point of view because you just write them down. No, you don't have to open up the Rita Schwinger paper ever again in your life. Okay, so that's if you ever did. So the only challenge involves the case where these masses are equal, as I said, because this object x is not local, and it's exactly the problem we had before. If you compute the residues on one channel, you get poles in other channels, and it's not obvious that it works. However, a big difference from the massless case is that here we've shown that you can do it. No matter what the couplings are, there's a concrete formula, very simple formula, It takes some notation to describe it, so I'm not writing it down, but there's an explicit formula for the most general 4-particle amplitude given the most general 3-particle amplitudes you can have. There had better be, oh boy, there better be, because there are massive higher spin particles in nature, like you and me, okay? Never mind nuclei and other things like that. There had better be scattering amplitudes for these things. So with this formalism, it's really possible to teach a field theory course now that covers the standard model and do everything. I mean, not everything in field theory, but everything in an introductory field theory course without ever mentioning a Lagrangian, including the Higgs mechanism, including one-loop calculation, computing the beta function, and so on and so forth. Okay, so I just say that because in many talks I've given over the years on amplitudes, people say, well, can you do this for the standard model? You say, probably. And anyway, it's very easy, as I said. Yes? That's hard. This is all, but a typical first year quantum field theory course is perturbation theory. So I'm doing perturbation theory, okay? So I'm doing perturbative quantum field theory. You can do without ever talking about a Lagrangian. And really everything, like including the Higgs mechanism, including running, all that stuff. Just so you see an example of what the answers look like, here's what Compton scattering looks like in this formalism. So for spin 0, a half, and 1, so you see very, very simple formulas. Well, what I just want you to notice is that there's no gamma matrices anywhere here, okay? So once again, everything just depends explicitly on the physical degrees of freedom, and so that's it. But if you go to spin 3 halves, something changes qualitatively. You see that the formula is a little bit more complicated, and there are these masses downstairs. And indeed, if you take the limit of Compton scattering for a charged spin 3 half particle, a charged spin particle for NES, you find that it has a factor that grows like energy squared over m squared to the power of 2s minus 2. And that's how massive higher spins and the impossibility of massless higher spins merge together. Okay, so as you would expect, you can't take the massless limit, and this is the most, I think, direct physical way of seeing why massive higher spin particles have to be extended objects. Okay, you literally cannot have an amplitude for a spin 3 half particle, charged spin 3 half particle, or any spin 2 particle if you have gravity that makes sense to energies parametrically above the mass of the particle. Okay, so that's how it's consistent with the impossibility of the massless guy. All right, so now let me say a few things about the challenge of UV completion. Now that we know the general S matrix rules, let's go back. As we said, the gravity amplitudes are blowing up as we go to high energies. Well, very much like pion amplitudes or electroweak longitudinal W and Z particle amplitudes blow up as you go to high energies. That amplitude looks like negative S plus T. And here we know a way of UV completing it, okay? Purely playing a game of trying to modify this amplitude, we can just multiply by 1 over 1 minus s over m squared, 1 over 1 minus t over m squared, and that's fine. It fixes up the amplitude in the ultraviolet, and that's exactly what the Higgs does. Okay, that's the Higgs. So we then have to go check the amplitude involved, and all these guys are also okay, but of course all of that is okay. So that's the weakly coupled game that we'd like to play. Okay, we'd like to write down amplitudes that only have poles, which are fine, which are bounded by a small constant at high energies and fixed angles, and need to satisfy a few other rules. We only want to have pole positive mass squared. There's a requirement of causality that tells you that at fixed negative t and large s, the amplitude has got to be bounded by s squared. This is an ancient argument going in other guises to the 1800s. It's all of your electrodynamics textbooks where you prove that the index of refraction has got to be bigger than 1. This rules out dumb form factors. Like if you multiply by e to the negative s squared plus t squared plus u squared, it's like an easy way to UV complete anything, but these things run badly afoul of causality. Spreading things out in Euclidean space, back in Minkowski space, will spread things out both forwards and backwards in time and would violate causality. But the strong constraint by far is going to be unitarity positivity that tells you that on a pole in the S channel, you have to be able to consistently interpret what you see as exchanging a particle. The general, yes, and all of them you can find in this way. So they're the ones that are weakly coupled and the ones that are strongly coupled. So things like Technicolor are not here, okay? But Technicolor are strongly coupled. All the weakly coupled things, for example, I could add many poles downstairs. That would have been theories with many Higgses. Okay? There's one different thing that you can do actually, which is to have a different structure. Reverse whether you put the instead of putting the S over 1 minus S, you could put S over 1 minus T, and the other way around for the other guy. That also UV completes it. That corresponds to that corresponds to a large N, and therefore weakly coupled Technicolor-like theory, where it's Ramanujan's that unitarize that unitarize WW scattering. And those were also discovered by people. They're called Higgsless models. Okay, it's just that there, because they're spin 1 particles, then you're repeating the structure over again, because their longitudinal components get strongly coupled, and so you have to play the same game over and over again. But indeed, you can discover in this way all of the weakly coupled examples that anyone ever found, and you don't have to write down a Lagrange. I mean, you just everything that's consistent from the amplitude point of view corresponds to a theory you could have written. Yes, yes, absolutely. So, all right. So the main physical point I want to make is that, and this is all sort of just translating a lot of old lore into this sharp problem of the 2 to 2 amplitude, is that in any theory that has long-range forces, so we have massless STU channel poles, then that crucial requirement of positivity, factorization, means that it's impossible to complete with a finite number of massive particles. Just to give you an example, imagine you have phi cubed theory, and you want to fix it as it goes to high, you want to make it go down even faster with energy, okay? Just like we did with in the Higgs case, if I now multiply this by 1 over 1 minus S and so on, you see that the residue here has got to be negative. And the residue somewhere has got to be negative. You have to have ghosts. And what's the difference with the previous case? Here, the thing is that we have a God-given sign for the residue at low energies, because there's a massless particle, okay? And therefore, the completion means that something at high energies has got to have the opposite sign, whereas in the pion case, it was very important this low energy thing had a minus sign in front of it. It had a plus sign, you also couldn't complete it. That's one of these standard positivity restrictions on higher dimension operators. But because there's no massless long-range forces, there was no God-given sign to have. So it's really, any theory of the long-range forces is phi cube theory, Yang-Mills, gravity, is going to need an infinite number of particles and infinite tower of spins. Okay, so that's going back again. Now we know all the rules. We know what the rules for the 3-particle amplitudes are. And we know what the UV completion rules are, and so we can ask this question of whether it's possible to find such a theory with infinite number of particles and infinite tower of spins, which does the completion. What's new compared to the 60s here? In the 60s, people were obsessed with massive scalars. And now we know there's a continuous infinity of such theories, any large N Yang-Mills theory. So no way you're going to find a unique theory if you're playing that game. Now we're talking about massless gravitons. And here it's much more constraining. Especially, first, we don't know an infinite number of answers. In fact, we only know one answer, which is perturbative string theory. Secondly, we have these massive higher spin particles that we have to have, but remember, it's exactly gravity that makes the massless particles impossible. So we can't decouple, because we're doing gravity, we can't decouple gravity from the problem, and that's why it's going to have to be extra constrained in order for the high energy limit of the interaction of these guys with gravity to make sense. Okay, so let me just, so anyway, there's a very sharp conjecture that the only weakly coupled UV function of gravity is string theory. And either a proof or a counterexample would be totally spectacular. And maybe all I will do is now switch to jumping to the opposite extreme, jumping to the end, and just telling you what it looks like in string theory, and just emphasizing that the really non-trivial thing is the unitarity. If you take the Veneziano amplitude or the open superstring amplitude, you sit on a pole in the S channel for the massive states, then you already discover the critical dimension from the consistency of being able to interpret things consistently as exchanging already at the lowest level particles correctly. But there's this amazingly simple statement this very simple polynomial of cosine theta has got to be expandable in terms of Fourier series in cosine k theta with positive coefficients. And if someone handed you the answer and you wanted to check that it's true, you would have to derive this fact. And it's an amazingly simple statement. It's amazingly difficult to prove directly. The only known proof of this fantastically simple statement you can explain to a kid in grade 8 is perturbative string theory and the no-ghost theorem. So if there is another way of thinking about things, it had better come up with an alternative explanation of this fact. All right, I think that's probably all I have time for. Perhaps I'll just say one small thing, which is that you might have thought that, that the problem is so constrained that already just the massless scattering amplitudes by themselves would be unique, and you couldn't find another formula that was compatible with the rules, and that ends up being not the case. You can find interesting inheriting the magical positivity of those expressions from string theory, you can find lots of interesting examples of toy amplitudes. Here's a toy QCD amplitude. It looks naively like something that could come from a Zarge N QCD theory for pions. So it's an amplitude that looks like pions at low energies. At very high energies, it has a power law. It goes like 1 over s, but it has an infinite tower of stringy poles. Okay, and it's positive. So that just says that this is not enough. Just checking the consistency of the massless particle scattering is not enough, which is not surprising. We have to we expected that it's those Compton scatterings involving the massive higher spins that's really dangerous. So those are the things that you also have to check. In fact, versions of this also for gravity. You can have deformations away from the string theory answer with little parameters that satisfy all the rules, and are almost certainly there's no theory that accompanies them. All right, so the final lessons are positivity of string amplitudes is pure magic. As I just said, just with massless scattering, there are some deformations that inherit this magic. They're very unlikely to be consistent theories, and it's an indication that we have to look at consistency involving massive higher spin particles, and that's what we're starting to do. Now we know all the rules. We can go in string theory, compute the amplitudes involving the massive higher spin particles. We see these interesting new polynomials show up, and as you would expect, the positivity of these polynomials does not follow from the positivity of the previous ones. It's a stronger condition, and so that's the first hint that indeed there are more constraints involving the massive higher spin particles. And all right, so finally, I'll just say that there's a very general remark independent of this more ambitious program, which is that ahead of time we can make predictions for an infinite tower of higher dimension operators, signs of an infinite tower of higher dimension operators in any tree-level consistent theory like this, okay? I don't have to say it in terms of higher dimension operators. I can say it directly in terms of the amplitude. If I take this gravity amplitude, and as t goes to 0, there's the piece that has a pole, and then it has to be a power series in S with all positive coefficients. So this is an infinite number of positivity connections on higher dimension operators. And I think it's very likely that a lot of the convexity and sign constraints that we're seeing in gravity, especially beyond the two-derivative approximation, things like the weak gravity conjecture or the ability to deform entropy equals area beyond two derivatives, should ultimately be related to this infinite number of signs. All right, so let me end. There are some obvious next steps. It would be nice to extend the general formalism that I told you to any number of dimensions and to supersymmetry. Well, supersymmetry we're in the middle of doing. It would be very spectacular to understand where these positivities come from. That explains all sorts of other remarkable facts about these polynomials I didn't have the time to explain. It would be really good to understand what massive higher spin amplitudes exclude these funny deformations, which we suspect can't make sense, but it would be nice to see explicitly that in those theories it's impossible to make the massive higher spins work out. But mostly what I want to say is that I think that there's a lot to be done in this general subject, and we need a lot more theoretical data. And for the greatest S-matrix theory of all time, our understanding of string amplitudes is very primitive. And real string amplitudes, I mean, you know, general excited states on the outside, and really seeing what they look like. Not in principle we know what they are, but really understanding what they look like. Just to give you an example of how primitive things are, nobody knows in a useful way how to even label just the covariant spectrum of the bosonic string. Of course, we know what it is in the light cone, but what is it at the 279th level? What are the states? To label them in a useful way. That would allow us to, for example, compute what these numbers are for the 3-particle amplitudes. We don't know what these numbers are. If I knew what these numbers were, then I would give you a formula for expanding that big polynomial directly in terms of powers of k theta, but I don't know what the formulas are. And I think conceptually the most interesting question of all to me is that I started the talk by reminding you that the 3-particle amplitudes for massless particles are completely fixed by Poincare symmetry. Obviously in string theory we have an infinite tower of particles, and these 3-particle amplitudes are not fixed by Poincare symmetry alone. But there's some very specific thing that you cannot differ from at all, and a very natural question is, are they the answer to some other condition? And what principle fixes the string 3-point amplitude? All right, thank you very much. Where's your stick, Shiraz?
We decided it would be nice to.
All right, thank you. Sir?
Actually, very quick. First, is there insight? I mean, I guess we don't know that the 5 string theories exhaust the set. Right? Is there any indication here that there could be another one?
Well, I mean, presumably, we're very far from being able to prove the statement, but that would be something that would follow. If you understood all the solutions to this problem, then you would find the 5 string theories. But let me say maybe a small thing in this direction, which is a little
6 or 7. We've missed some.
Yeah, maybe. I mean, doubtful, but I'll say one thing which explains one feature of the string amplitude, which is pretty interesting, which is not completely obvious ahead of time. I'll even say it at 4 particles. First, there's only like 3 4-particle gravity amplitudes you ever get in any perturbative string theory. No matter how you compactify, no matter what you do, because things are independent of the details of compactification, they only depend on the worldsheet supersymmetries.
What about the possibility of optical?
But we don't have any known. We have no examples of weakly coupled warp compactifications.
Cannot exist.
No, it's not clear that one can't exist, but I'm just going on examples. Okay, so and asking Shamit. But I want to say something a little interesting about even the structure of the perturbative gravity amplitudes, which, as I said, not 100% obvious if you just stare at the Kobe-Nielsen formula or the integral formulas, which is that if you take, let's say, the heterotic answer, the heterotic answer looks like the type 2 answer. So let me say it another way. What differs between the heterotic and type 2 is that the heterotic has the type 2 has the standard 3 graviton vertex. Type 2 heterotic, because it has less supersymmetry, is allowed to have an R² dilaton coupling. Okay. Now, if you're a low energy person, you would say, okay, so let me compute the amplitude with 2 different kinds of vertices, right? There's the gravity vertex, there's the R² 5 vertex, and you can like build the amplitudes from the pure gravity part and build the amplitudes from the R² 5 part. And already at 4 points, we can even just talk about it at that level. What's interesting is that the amplitudes individually sort of thicken, gammify each piece. So they can be written as a gamma-thickened gravity part plus a gamma-thickened R² 5 part. Okay, that's not, and that appears to be the case at least experimentally. It appears to be the case at any number of points. That the different amplitudes you get from the different theories are really separate thickenings of what the massless of what you'd expect from the massless amplitudes in the low energy theory. If that's a general feature, then it would explain why there's a small number of theories that we could be talking about, because you're inheriting you're somehow inheriting the structure of the massless theories and thickening them into into things that are stringy. Then the finite number of possibilities for the massless theories would give you a reason to expect a finite number of possibilities for the massive.
I see. So my second question is, why should we have been so lucky? I mean, it could have happened that there was no weakly coupled ultraviolet completion of gravity, right? We could have had M theory and not string theory.
Absolutely, yeah, right.
We're just lucky, or what?
I'm not.
There's nothing logically wrong with that, right?
Problem. And it's just like it turns out that there are CFTs that are intrinsically strongly coupled, and they're not limits of things that have a weakly coupled description. Maybe there are isolated. It's true that the theories that we know so far have strongly coupled. Have places that don't have a good stringy description, but they're continuously connected to ones which have a perturbative description. Maybe that's just because we're lucky, or even not lucky. It could be a classic lamppost effect because we started off like discovering them in the weakly coupled regime, and